internet is actually completely screwed up. I'm going to try to fix that when I get back. So I don't have video number 7 up yet. I thought about this and thought about it and thought about it, and I've been trying to think of a way to re-express what I talked about last time. What I talked about last time was that Boltzmann figured out this thing about probability density. Now, we talked last time about probability. You understand probability, you understand the flip of a coin, but that's not how really nature works. Nature does not work that way. We teach you that as children because it's easy, but that's not really how anything happens. So Boltzmann figured out this probability density that works kind of like this, and I'll express it in terms of velocity. Probability density times a certain change in velocity is actually the thing you understand. That's actually how nature works. Nature sets this up, and then it says, well, there's an actual spread. But when I have a partial, either I have to take another partial and divide it to get a derivative, or I have to integrate it. It's one or the other. It doesn't make sense otherwise. Otherwise, it's 0, right? So remember that these things have units. That's actually one of the answers to one of your homework questions. Or is it on the test? Oh, that's anyway, these things do have units, but by themselves, whatever the units are, this would be velocity, this would be meters per second. Its value is 0. So it doesn't make sense unless it's integrated, and then we can integrate it over some certain range. And let's do 0 to infinity, and that would be 1. That means that it's probable that a molecule is either moving or not moving. That's what that says. That's the answer to the question. Is a molecule moving or not moving? Yes, it is. All right, so we get that. Now, the thing that was kind of a bisnobber was that Boltzmann derived this formula. All right, so he said energy of a certain, speed, and we have to divide that by kT, otherwise it just doesn't make sense. Otherwise, we have e to the units, e to the joules, and we can't. That's crazy. That doesn't make any sense. Over all possible energies that a molecule could have, and I went over a little bit about that quantum mechanics thing, that things have energy levels, kind of like those SPD orbitals that you learned about hydrogen atoms, kind of like that, but I'm telling you it applies to everything. That's the thing you haven't learned yet, but you're going to learn it in 344, and I'm kind of previewing that now. So this is what Boltzmann said. Now, I'm speaking out of my ass in all honesty because I didn't really write down notes because I'm just trying to get across to you as well as I can. So this bottom part ends up being m over 2 pi kt to the 3 halves, and that was a standard integral. It was to the 3rd power because we live in 3 dimensions. And then we had energy, which is 1/2 mv squared over 2 kt. Okay. Now, sorry. Let me do something I promised I would never do, which is write over my own work. This is where I kind of feel like I don't know that we were connecting too well. Mvx squared plus vy squared plus vz squared over 2 kt. Okay. So this is the part I wasn't really feeling like we connected too well. Now, again, I'm going to have this partial deal, or it doesn't make sense. And I live in 3 dimensions, so I have to do partial v, y, and z. Oh, why did I do y twice? I'm an idiot. There we go. That looks like a 2. I should just check myself into the asylum anyway. So there you go. Okay, now this is as is. All right, now this is Mother Nature. Now, what I really want is, you see, this isn't so great. I mean, I live in 3 dimensions. I don't have a choice about living in 3 dimensions, but nature doesn't see it that way. Nature doesn't know up, it doesn't know up from down. I mean, from left and right, that doesn't make sense. Nature likes just net velocity. And what I said was, well, here, I guess this is a big old therefore, right? Therefore, m over 2 pi kt to the 3 halves, I almost wrote 3 halves, kt 3 halves, e to the minus mv squared over 2 kt. Okay, I recognize that that's velocity squared. But I end up with this damned problem of these partials. All right, so I can't live with this. I can't live with this. This equation doesn't make sense in the present form. I have to turn this bad guy into a partial velocity. Otherwise, it just doesn't make sense. Now, what we did in the second hour, which I did not post yet, I'm trying to post it, the freaking computer froze. This is where my memory card is. So my computer trying to upload that video, is how I turned that into spherical coordinates, which then ended up being a function of velocity. There we go. And I'm not too destroyed, so there we go. So I went over how to do the transformation, but I don't know, that was the part where I really felt like our conversation just kind of started losing it. So I want to express it a different way. So in other words, the whole point is, how do I turn that into velocity? That's what I'm trying to do. All right, let's look at a function, and let's integrate it. Let's integrate this bad boy. Let's go from 0 to 100, and terrible x. And anyway, it's a function that looks kind of like that. And I want to integrate this thing. I don't even know what it is. Whatever. It doesn't matter. What I want to do is Simpson's rule. I'm going to take a step size. I'm going to take a step size, which will be this thing here, which you're pretty familiar with, hopefully, at this point. I'm going to take a step size and calculate an area. And then I'm going to add up all the areas. All right, Simpson's rule. And I did this, I talked about this a little bit last time. I don't think I really did a good job, blah, 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 blah. Anyway, rectangle, 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 rectangle. And it turns out that, let's see, we're going to do the integral from 0 to 100. So this is very concrete. I've got this function, and I've got a certain set size. Now, when I was your age, when I saw these integrals, I was always kind of like abstract, kind of like, well, okay, do I get it, do I not get it? When I actually had to sit down and calculate it, then I understood it. And this would be a certain number of rectangles. The number of rectangles will be 100 over this partial, starting at n equals 1. And these are the number of n's, the number of rectangles, which is hopefully obvious. And then I've got data. I've got data, which is a certain function of the step size. And then I've got that times the step. And the smaller that is, the better my results are. That's kind of the whole point. Okay, so I think we all understand this. Hopefully we had all this in high school. But we're not in high school anymore. Now we're going to live in 3 dimensions. And that's going to change things. All right, so this is 1 dimension. Let's go to 3. 3 dimensions, x, y, and z. And fortunately, I can actually draw okay. My memory of remembrings. Memory chips is not so good, but anyway, so we got x, y, and z. Okay, now I have to take a step. But I have to take a step in x, y, and z. All right, what that's like? That's like this. Okay, let's go to x. Again, I've kind of drawn that a little off center just for the hell of it. And let's go into y. And let's go into z. Okay, x, y, z. Just took a step. But I did it in 3 dimensions. All right, now I'm looking at that and I see this. I see a cube. Excuse me, I see a cube. Right? Isn't that kind of obvious? All right, so it's a volume element. So when I do an integral in 3 dimensions, when I do this bad boy, I'm actually doing this bad boy. I'm multiplying. This is a volume element. This is this. And this is volume. That's exactly what it is. Now let's make it bigger. All right, that's the whole point. Let's make it really big. And we're going to test in a big way my ability to draw. So don't draw this until I'm done, because I don't know if I can pull this off or not. I'm going to try my best. Okay, so I'm drawing a brick. Is that brick? Anyway, oh, you're too young to know that song, aren't you? Anyway, yeah, some of you know it. So I am doing a very lame job of drawing a volume element that's gotten much bigger. Here you go. And this is more dx, dy, dz. That's what's happening there. All right, so my point is that this guy is its volume. And you can imagine, now I've drawn this in a very crude way, but it's kind of looking like a sphere. Badly, but it is. All right, it's a sphere. And that means that this volume element isn't quite the volume of a sphere. It's actually the volume of a shell, of an eggshell, except the egg is round. So, what can I do with this? All right, so now, okay, I hope you have this down. If not, don't worry about it. Hopefully we'll have a video. All right, again, what do I do with this sucker? Now, last time, again, in that second hour, I did it exactly. I drew this out. I transformed this SOB exactly as it should be done mathematically. I'm telling you, there's another way to think about this. There's another way to think about this like it's the volume of an eggshell, because it's a volume. And how do I do that? Let's see. In XYZ, I'm going to do XYZ again. And this is going to be kind of crude. What I've got, again, that horrible terrace-looking thing is kind of sphere-like, kind of. But if I really do, you know, the little partials like really, really small, then it's definitely sphere-like, and it grows. It grows like the volume of a shell, and it grows by. Sorry, this is kind of crude. It grows by this. It grows by the partial of volume. Okay, but how thick is it? How thick is it? Well, what I would have is area times thickness. And that would be the volume of the shell. Sorry, my handwriting's bad today. Okay, now thickness I already got. That's dV. Area, what's the area of a sphere? Anyone? Shocking how many of you got that. 4 pi v squared. Right. The area of the sphere times its thickness is the volume of the shell. The volume of the shell is exactly what that is for the reasons I've drawn here. Okay. I know it's kind of hand-wavy, but there you go. So, this SOB ends up being, I'm sure it's not working today, m over 2 pi kt, that's terrible, kt, to the 3 halves. Now remember that's the normalizer, 4 pi v squared e to the minus mv squared over 2 kt dv. There you go. And that's the Boltzmann equation. Everything you need to know about it, except for all this other bullshit I'm going to talk about for the next 2 or 3 lectures. Anyway, so there you go. That's everything. And now we talked a little bit last time. One of you nailed it. You know, what do I do with this thing? Well, this is the Maxwell-Boltzmann. Boltzmann got his part here. Maxwell figured the rest of this out, so it gets Maxwell-Boltzmann. And I know that if I integrate, don't even write this down, I don't really care. I know if I integrate from 0 to infinity, and I'm asking the Maxwell-Boltzmann, I'm asking the probability density, I have to give it a partial, otherwise it doesn't make sense. If I have a partial, I have to integrate. If I have to integrate, I have to ask the question, how far, what's the probability that a molecule is either moving or not moving at all? Other way. Anyway, and the answer is 1. There you go. That's a probability density. Something's moving or it's not moving at all. And that's pretty easy, right? That's very simple. And I'll even have you, I think I actually have this on the next problem set. I'm going to have you actually solve this sucker and show that exactly 1. Now, again, to keep anxiety down, just want to let you know that when it comes to all Maxwell-Boltzmann questions, which I'm going to ask actually a quick ton of, your next test, half, default at this, pretty much. Every one of these integrals that you have to solve, you're given. Because I know you can look them up already. I already know you have them in your calculator. I already know that you have the internet on your calculator. So trust me, it ain't gonna matter. So I'm gonna go ahead and give you the answers to all of the questions I'm gonna ask. You still have to use it. Okay. All right, so anyway, what do I want to talk about this? Let me go over certain properties of this bad boy. It isn't really kind of obvious. Getting behind myself today. Help I screwed up my freaking camera. Question?
I just want to know if 4 pi r squared or 4 pi v squared.
4 pi v squared. 4 pi v squared. V is r.
V is r.
So as you have been kind of drilled in your head, and this is something I want you to try to get over, and I know this is true of all of you, it is true of absolutely all of you. You're used to r, theta, phi, you're used to x, y, and z. Well, I'm just not using those letters, all right? So, so v is the net. It's r and you know, r, theta, phi. It's the same thing as r, I'm just using v, it represents velocity, all right? So anyway, and that's going to get cemented as we use it over and over and over and over again. Let's do some properties first of this thing. Properties. One is that the Maxwell Boltzmann probability distribution is proportional to v squared e to the minus v squared. Okay. Now, what that means is, now this isn't Huffy the Puffish. All right, you have to understand there's limiting forms. If velocity is 0, then the probability is 0, because I have 0 times blah. I don't care, it's 0. But if velocity equals infinity, infinity squared times e to the minus infinity squared, guess which one wins? Huh? That's actually a question. Right, it's e to the minus infinity, so that's also 0. Number 2, and again, that's in Huffy the Puffish, that's why I actually had that in there, because of exactly this. The probability of having a certain speed is proportional to mass to the 3/2. Yeah, there we go, mass to the 3/2, e to the minus mass. E to the minus, there we go. Here we go. So that means that at large mass, the fact that something would be moving is 0. All right, that's pretty simple. Again, if you're heavy enough like me, you're not going anywhere. Barely made it into work today. Anyway, that was a joke. Anyway, so other little tidbits that I have here. Let's look at the probability distribution. Actually, sorry. Let me say that. Let me put it this way. In the Maxwell-Boltzmann distribution, because I do have this on some of the. Let's see. I'm not sure whether I'm going to have this on a homework set or on an exam, but it's relatively easy. Okay, so this is 0.003. So I have actual numbers, and this is 0. And this is 500. This is velocity, and this is being meters per second. And handwriting's pretty bad today, sorry about that. It's 1500. And let's look at argon. Okay, so this is argon, and this is at, let me see here, you're right around here, around 298. This is at 298 Kelvin. And if I go to 100 degrees C, it ends up being something a little more like this. So that'd be 398 Kelvin, okay. So this is the probability. Maxwell-Boltzmann represents a probability of having a certain speed, given a certain mass. I decided that here, given a certain temperature. And I see that as the temperature increases, the average velocity tends to increase, which is, you know, blindingly simple. Right? That's very, 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 very easy to understand. Okay, next example, and then we're going to get into some things that are really kind of kind of painful. Hopefully not too painful. Let's do Maxwell-Boltzmann. Again, this is the probability density. Again, I've run data. This is around on the same scale, so that's about 500. So this is velocity in meters per second, and this would be around 1,500. Right around here. Now it turns out that okay, right here. This would be krypton. Now, here's the damage. Now I'm going to compare masses. Now, I like to use Nobel gases because Nobel gases are easy. If you can't understand a Nobel gas, then there's kind of something wrong with you. Okay, krypton is light. Argon is lighter. And so, as such, argon has a faster speed. This is all at the same temperature. This is all at 298. Okay, all at 298 K, and this is argon. Again, argon is lighter than krypton, and what's lighter than krypton is neon. And that has a distribution like this. And sorry for the crappy drawing, but do the best I can. That's neon. Okay, now, this is one of the answers to your homework questions. It turns out that all gases, or everything, including us, because we're gases, anything, the blackboard, my shoes, me, you, the water in the air, we're at the same temperature, hopefully, or something's really screwed up. We're at the same temperature. Now that means we have the same energy. If we have the same energy, but you're lighter than me, you have to be moving faster, right? 1/2 mv squared. So if we're all going to have the same energy, this is one of the fundamental tenets I'm getting to that I'm going to prove a little bit later. I'm just previewing it right now. We all have the same temperature. We all have the same energy. We all have the same energy. Lighter things have to go faster than heavier things. They have to. That's that 1/2 mv squared balancing each other. So anyway, that's just kind of, the central thing that you should get in your head. And even if you don't, it doesn't matter. It's right in there, right in there. It proves it. Plot that bad boy. You'll find the same thing. I mean, this is where I got it. So anyway, fundamental things about Maxwell-Boltzmann. Okay. Now this is where this is good. I always hate this day. This is where we're actually going to start to use this thing, and yeah, it does. Free of a piece of paper. New piece of paper. Start at the top. What do we do with this? Why the hell am I talking about any of this anyway? What am I talking about? Well, longer than let me tell you what you do with probability distributions. All right, so I've gone over the whole idea that something is either traveling or it's not traveling at all, and that's kind of easy to get. But obviously there's more to it, because I already know that. I already know that something's moving or it's not moving at all. And those curves are nice. I mean, that's something new. That's information I didn't have before. But is there more to it than that? The answer is yes. It turns out that if I can find my fucking notes, I can tell you something. So, you had this in calculus, but the more I interact with you, I know it's been a while. All right? But when you want the average value of something, let's say we want the average value of velocity. Let's say we want that. Okay, you had it in calculus. So I know it's been a while. It turns out you integrate the distribution times that thing you want the average value of. Now again, you had it in calculus, but it's been a while. I'm reminding you that this is how all things work. Now, of course, Maxwell-Boltzmann requires a partial, and there it is. And partials have to have integrals, and integrals have to have limits. So now I know that in terms of net velocity, the net velocity could either be 0 or it could be infinite. And don't forget that those would have units as well. You may notice on the last homework that I'm really obsessed with units. It's kind of important to get this kind of stuff done. So anyway, Alrighty then, so there we go. That is the average velocity of a thing. Later, we're gonna get into average velocity squared, because 1/2 mv squared is energy. And then I know how much energy something has. And then I understand thermodynamics. Thermodynamics of gases. Then we'll do thermodynamics of proteins, but we're getting there. It's gonna be a while. We have to start here. We have to start somewhere. We have to start simple, right? I think you all appreciate that. Except that this is a bastard. Oh, God, don't hate me, but this is what's happening. All right, so you know that we have a function, and we can cast it in this form. We can solve it this way. You already recognize it, right? Integration by parts. Sorry, this is why. Now you know why I brought it up in that first extra hour. Okay, this is how we're going to solve this. So take that freaking Maxwell-Boltzmann distribution that I just wrote, multiply it by velocity, and then cast it into this form here. I screwed it up. Cast it into this form, and this is the solution. Oh, if you think the next 10 minutes aren't going to blow, then you're an idiot. Anyway, so let me write this sucker down. And you folks tell me if, you know, maybe during office hours would be better if this just doesn't connect. I'm gonna try to do the whole like I'll work downward thing and I'll toss the blackboard up. I hope that works, but that's what I'm gonna do anyway. Okay, so this thing. Now I know my limits are 0 to infinity. I've got this 4 pi m over 2 pi kt. Oh, my handwriting has magically improved. Now, the thing that you tend to forget on tests and homeworks is I've got this v squared that comes from the volume element, but I'm multiplying it by v. Now I've got v to the third. And then I've got this e to the minus 2 pi kt. What am I doing? Minus 1/2 mv squared. Minus m v squared over 2 kt. Sorry, when I try to do things off memory, I often screw up. And sorry, my velocities are always, I never draw things the same way twice. It's just weird in that way. Okay, now I remember when I was your age and I was doing undergraduate research, and I was presented with a Fourier transform, actually. It was an equation 10 miles long. And I told my advisor, I looked at it and I said, no, I can't do that. I can't do that, that's above me. And he looked at me and he said, no, you're an idiot. That's the problem. And I look at this and it looks fearsome and scary. Reality is, this is just a bunch of constants. Just a bunch of constants. I mean, I'm sorry, can you not plug in 32 kilograms per mole times pi and take that to the, you know, hit that little magic button to the 3 halves? Can you not do that? Yeah, you can. You do it just fine. Right? So this is actually really quite easy. So already a large part of this is already gone. It's just a little number. It's a number. All right, so then I know that numbers go outside integrals, and already it's much easier. Now I've got this bad boy. I've got the v to the 3, mv squared. Again, my v's are never the same. dv. What am I wrong? What's wrong with me? dv. Sorry. Just had a brain explosion. Okay. Not bad. That doesn't look so bad. Now, again, I'm going to try to just kind of work linearly down the board. I hope that this isn't annoying and goes across well. Now, I've got to figure out what this guy here is. And now this is really, really counterintuitive. It's just that I already know the answer. You know when I already know the answer, I can set it up to work. And the answer is that f, you may want to make f a b to the 3. Intuitive, but wrong. Again, why? Because I already know the answer. What we're going to do, okay, again, I'm setting this up. F is going to be b squared, right? And that makes that makes the derivative 2b. Okay. Sorry, again, I'm setting this up in a way because I know I can solve it. Okay, now that makes the derivative of this part. I have to figure out what this part is, and that's kind of obvious. That's going to be velocity e to the blah, 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 and v squared over 2kt. Let me double check that's actually correct, and that is correct. Okay, then I have to figure out what g is. Therefore, g of velocity is going to be kt over m. Is that going to be minus? Yeah, it's going to be a minus kt over m. Okay, again. Oh, I hate integrals. I hate them. I have to figure out the derivative of what? The derivative of what is this? And I can see that when I have the derivative of an exponential, the argument pops its ass back down. All right, so this is why I borrowed one of the v's from f. I borrowed it because when I do the derivative of this sucker here, minus mv squared. Sorry, this is ugly. Hope this is visible. I can see when I do the derivative of this sucker, it turns into that. Right, and so that factor of 2 also is been eaten up, in case you're wondering by this. Oh, that looks ugly, doesn't it? Sorry. Obsessive compulsive, anyway, there you go. Yeah. Take the derivative of this and you get that. This times that is that. There you go. We're set. All right. Now, let me go ahead and keep working this thing, and I'll just work again linearly downstairs. So I know the average velocity of something, function of mass and temperature. And what do I got? Question?
One thing, why derivative of, how g prime and g is related, one more time?
Well, now this is my notation. This is a derivative, and I have a prime. Now, remember that integrals are derivatives in reverse, and that's what I hate about them. But it's how it is. Okay, let's take the derivative of this sucker with respect to v, because that's our integrand. All right, so I would bring down that derivative of an exponential returns the exponential. Boom. It always just returns. But then you have the derivative of the function inside. The derivative of this sucker here is going to be minus 2v over times m over kt. Times kt over m returns just a positive v. All right, so again, the derivative of the inside times this is that. There we go. It works. Works just fine. Any other questions? In the office hours would be better. So anyway, and again, this is all meant to go into this bad boy right here, because that's just what it is. And what do we get? Okay, so average velocity ends up being, I don't know time, terrible, ends up being q. Again, a bunch of constants that I don't really care about. I can throw it away. I can't forget them, all right? They got to come back. But for now, they can just stay. Q. Now, this is where it gets a little painful. Okay. Okay, I got a v squared. That's the f part. I'm looking at that right there. I'm looking at that. V squared. Now let's do the g part. Minus kt over m. E to the minus mv squared over 2kt. Okay, now a part that is not really expressed very frequently in terms of integration by parts is that this part actually has limits. And don't forget what the limits are, 0 to infinity. Okay, that's the first part. That's this guy here. It's easy to forget that that guy has limits. It does. It's just not often expressed. Minus the integral and again 0 to infinity of, let's see, I've got f prime, so that's v, 2b. Okay, I'm looking at this bad boy right there. I'm looking at that, I'm looking at this, 2b. I've got g again, minus kt. Sorry, I found out right out of the state question. Your question? No questions?
Yeah.
Video's given out.
Mine's still recording, so.
Oh, you got a second recording?
Yeah.
Okay. Again, it's funny, like the first time that this ever happened, I noticed a student was holding up their iPod or iPad or whatever the hell. I'm glad that guy's dead anyway. Was he a genius or was he a monster? No one ever knows what Steve Jobs really was. I mean, you always see these videos like he was this great guy who came up with the iPhone, and then you hear that he was a monster, and you never really know who he really was. And I don't think he was actually country. That's one thing I do know. But anyway, iPhones are kind of cool, though. I don't have one. Why am I talking? I really need to learn from him to shut up. That's my main problem. Okay, so now we're doing this middle part, and I've kind of run out of room, which is why I'm writing kind of funky. E to the minus mv squared over 2kt. Yeah, I'm sorry about this. I stupidly wrote myself into a corner. Anyway, I just did this. That's all I did. Okay, now this guy's kind of easy. Let's see. Upper limit, e to the minus infinity. Now I've got infinity squared. I already went over this. Infinity squared times e to the minus infinity. 0. Minus 0 on upper limit, minus the lower limit. 0 times, who cares? Doesn't matter, 0. This is a mistake. It's a mistake. Sorry. Oh dear God, guys, I'm really sorry about this. Tell you what, handout. I'm already in the handout. I'll get a handout on this sucker. I'll write it when I get back and upload that freaking video. Q has to multiply the whole thing, right? So I put a bracket in the wrong spot. Okay, this guy's going to be 0. 0 minus 0 is 0. All right, I got that part. And then this is a minus sign, right? From there, it's right there. Okay, sorry about that. Anyway, I'm going to give a handout on this. So if I've gotten too wonky, then that's fine. Well enough. Okay, so now what have I got left? I've got minus. I got a 2kt. Okay, minus 2kt over m. And, well, I've got a q times that. Well, that's an ugly looking q, isn't it? Here, let me draw it prettier. Okay, I've got the q. Just a bunch of numbers, a bunch of other numbers, which I know. I've got 0 to infinity, those are the limits. I've got a unit of velocity, and I've got e to the minus mv squared over 2kt. Okay, I've got this guy here. Okay. Now here's the damnedest thing. This is kind of cool. You may recognize this. Hopefully my handwriting isn't too terrible. Recognize that? It's right there. Yeah, it's right there. All right, I've already integrated. All right, this is an integral. I've already integrated it. It's right here. All right, so let me toss that up and continue downward on our average velocity.